Namaskar. Good afternoon, everybody. Coming after Udayji's talk is very exciting because you gave insight into today's technology in a very beautiful manner. Thank you. So, there is a pun on the word complex. Can somebody guess what it is? The hint was already given earlier this morning in the first session when I said that mathematics is important. And I said that I will be talking about it in my technical talk, which is now. This will change the slides? Okay. So, can somebody guess what the pun is? Complex modeling. What do you think complex is? Anybody? I've given a hint that it has something to do with mathematics. I'm going to talk about complex numbers, but we'll come to that. So this is, I'm presenting this talk on behalf of a collaboration we have between India and Canada. Ajay, Soni, the blue are from India, me and Ajay Soni. Ajay Soni is from IIT Mandi. And everybody in the red is from the University of Western Ontario in Canada. So this collaboration has been supported to a large extent by the Shastri Institute initially. So, okay. The middle one? Here. So congratulations once again to all the organizers for a very important meeting on sustainable innovations, advanced materials. So in this meeting you're going to hear about many things, and let's see, you will, I'm sure, hear about nanomaterials, nanotechnology, nanoscience, and these are the materials of today and tomorrow. Carbon nanotubes, graphene. You will also hear about biomaterials. Some of these will be replacing living organs in the human body. Some of us are probably already have these. I often run into people with lovely black hair, but that's not real. We meet people who are as bald as me, but they have nice hairstyles. Many have false teeth, but there are many other organs which can be replaced by biomaterials. Aerogels are going to be very important. You know, they are amongst the most difficult systems to investigate are gases and liquids. Means certainly solids also, but gases and liquids, because they do not have an extended structure, which is crystalline, which is a regular structure, that makes it very hard to understand gases and liquids. And aerogels combine these properties of gases as well as liquids. Then you have metal foams, which are coming up. So these are metals. They have flexibility, porosity, which gives them unique properties for applications in technology. Optical fibers, Udayji talked about it. There are young students over here. I would like to ask, can you name two Indians who have contributed enormously to optical fibers? One of them should have actually got a Nobel Prize for this work. Anybody? Dr. Narendra Singh. Now please Google and find out what is his contribution to optical fiber technology. He has made fundamental contributions which are so important that many people think that he should have actually got a Nobel Prize for this work. The other is Pancharatnam. Pancharatnam was a student at Indian Institute of Science. He studied under the supervision of C.V. Raman. And there is an important phenomenon which is known as the Pancharatnam berry phase. The Westerners normally call it only as the berry phase after Michael Berry. But it is based on the same idea which Pancharatnam developed in the context of optical fibers. And it is going to be of even more importance in the coming years because a technology to build quantum computers, the qubits are very unstable, they are very fragile, and to develop more robust quantum computers, you may need to use the idea of the Pancharatnam berry phase in an innovative manner. Then you have materials which are called as shrills. These are made from shrimp shells and biomaterials. They will have applications in surgical applications, medical technology. Then the two-dimensional materials, semiconductors, insulators, superconductors. So there will be very fascinating developments in this area. And then metamaterials. Metamaterials have very unique electromagnetic properties, electromagnetic and optical properties, where you have very strange behavior. You can have negative refractive index, for example. So these are some of the materials, and I'm sure that there will be some talks covering some of these areas and perhaps some more. There are lightweight materials which are very light, and their strength comes from hydrogen bonding. And these are polymers, polymides, and long chains of hydrogen bonded materials. Then technology is growing in the area of, where everything that you look around, there are colors. I mean, there are these red colored chairs. Everything around you has got colors, and colors are very toxic. How do you produce these colors? So this is where you need an ethical technology, which is what is meant by ethical colors. So this is coming from bacterial dyeing. And the bacterial dyeing, this technology is coming up in a very big way. It is scalable to the extent that it can meet the requirements of the society. It is 80%, it uses 80% less chemicals, which is really what makes it sustainable. It uses 77% less water, and it causes fewer than 31% of carbon dioxide emissions. So these are the things which are moving in the direction of sustainable technology. This is grown in bioreactors of this kind. And then you need different kinds of materials. In particular, I'm going to talk about the kind of material that is required for defense. And we have DRDO, Dr. Sushilji with us. So some of this work may be carried out in your labs as well. We have lost 2,000 soldiers at Siachen, and due to bad weather and such things. It's a huge loss. A single soldier life is something which causes, in the amount of pain it causes to every proud Indian, is huge. And we have lost 2,000 of them just because of weather and climatic conditions. So how do you clothe your soldiers? Now the clothing should protect them from weather and also from bullets. So you need multifunctional clothing. And you need special materials for that, and I'm sure DRDO is engaged in extensive research on this, materials which combine the properties of metals, polymers, ceramics, composites of various things. So these are huge requirements of the future of generating multifunctional materials. Then you need energy, and you turn to batteries, but materials for batteries are scarce. Materials for fuel cells are not, so fuel cells, research in fuel cells is a very important domain of engagement. And then you need materials for quantum computing. Now, perhaps many of you are very excited about quantum computing, which is around the corner. It is already with us. Right now, there are very few quantum computers, but in another 5 to 10 years, there will be many. And you will continue to use classical computing, but in a different way. But the main challenge in quantum computing is that the qubits are very fragile. There is this problem of decoherence, and you can lose the entanglement very easily. So you need new materials for the hardware platform for quantum information processing. And if you just demonstrate the concept in the laboratory, that is not enough, because you need scalability, which is a huge challenge, and that is extremely hard in the field of quantum computers. So proof of concept research can in fact be misleading in this area. That is due to decoherence, as I mentioned. So fossil fuels, we will probably run out of these in 40 to 50 years. We will run out of natural gas. It's maybe certainly not going to last us more than 100 years. So how are you going to meet the energy requirements of the world? And then these fuels, fossil fuels, natural gas, they cause enormous pollution. Means these pictures are not, they are seen every day when you commute in Delhi or anywhere else in any city. So you need to mitigate this situation. You need new materials which will provide energy. And it is not easy, because we have from the earth enough for every man's need, but not for every man's greed. But these needs are growing all the time. You need novel materials for more energy, more electricity consumption, which is what this conference is about. And would it not be nice if you can convert heat into electricity directly? Because heat is generated, it is sometimes called as the most degraded form of energy. Because whatever you do results in some heat, some energy dissipation, and if you can convert it into electricity, that would be great. And it is this work that I'm going to be talking about, which is the focus of today's talk. And it will be driven by these two kinds of materials. One is the solar cells, and the other are thermoelectric materials. So here, solar cells and thermoelectric materials is the main area of our research collaboration, which I mentioned earlier, between India and Canada. The thermoelectric materials, you can have them on your wrist. You can have them in flexible form. You can have an energy management IoT tied up to that. You can have Bluetooth devices, and with this you can have real-time health monitoring and so on. So these materials are of great importance, and what they rely on is conversion of heat into electricity directly. Now, you need high performance thermoelectric materials. Basically what you're doing is all the waste energy, means you're burning some energy, some heat is being generated in your body, and you're trying to convert it into electricity. So instead of letting it go waste, you harvest it and convert it into electricity, and you need a material which can do that, and that's what I'm going to be talking about. Now, all this is very difficult to do, and look at the last line here, that the challenge comes mainly from the fact that there is lack of a good research roadmap. And this is where research is really challenged. And what you want to do is, you can't take up different materials and keep experimenting, find out does it work or does it not work. Okay, if you want a drug for cancer, for example, you try different drugs and you don't know what kind of a molecular structure the drug should have. So the alternative is to simulate this. So simulation has become a powerful tool, and you need to simulate materials with desired properties. And this is where modeling, mathematical modeling of drugs, or in this case, mathematical modeling of functional materials, advanced materials for sustainable innovation, you need to come up with very robust mathematical models. And I'm going to be talking about complex modeling, in which the word complex refers not just to the complexity, but to the use of complex numbers. And complex numbers, everybody, now that I have told you what the pun is about, complex number is a pair of real numbers. So if x and y are real numbers, x plus iy is a complex number. I is imaginary, it is square root of -1. But there is nothing imaginary about the imaginary number. The imaginary part of the complex number is as real as the real part, because it is a pair of two real numbers. It gives you the capability of handling two real numbers in one go in an algebraic scheme. That is not enough in quantum theory. That is not enough to describe nature. Nature requires the quantum theory. And quantum theory requires the complex numbers. It cannot be built by two systems of real numbers. You need a complex number at a very intrinsic level to build the quantum theory, but that's a much larger subject. I want to focus today's talk on solar materials and the thermoelectric materials. I'm going to talk about a mapping which is from a complex number Z to another complex number W, and this is a mapping. The WZ, e to the power WZ, WE to the power W is Z. This is a mapping, and this has got a countable infinite number of solutions. This mapping, the function W is called as a Lambert W function. And this function has got very exciting properties, which provides the basis for our work, which is on the basis of the Lambert W function, there are number of branches in the complex plane. The branches with k equal to 0 and k equal to 1, these are real values for any z. You have a principal branch for k equal to 0. This has got positive values in its range. The branch with -1 has got this range in its closure. This is a plot of W0 and W -1. And what this function does is something that I'm going to tell you. I will not get into the mathematics in too many details because it will not be suitable for this audience, but I wanted to let you know what this work is about. So here is some work which has been done by my Canadian collaborators, Kenneth Roberts and Sriram Valluri. They've studied this Lambert W functions. Those of you who have studied quantum dots, there are people over here who are studying quantum dots, nanosciences, nanotechnology, quantum wells, quantum dots, and quantum wires. May be familiar of the problem of a particle in a box, in a spherical box. And the quantum solutions for this do not have analytical solutions. You have to get the solutions either using numerical methods or graphical methods, but one can use methods of complex analysis, and this has been proposed by Ken Roberts and Sriram Valluri in a paper which is not very old. It came up in 2017, and they showed how to get the solutions using the Lambert W function. Now, what the thermoelectric effect is, how it gets used in designing the thermoelectric effect, because you need efficient thermoelectric materials for sustainable innovations. So everybody knows the Maxwell's equations, I would hope, or at least is familiar with the Maxwell's equations. And this is the J equal to sigma E complements the Maxwell's equations. Maxwell's equations tells you about the fields, but then when you come to currents and fields and how the fields determine the currents, the J equal to sigma E gives you that relationship. And that is coming from a voltage difference, that when you apply a voltage difference across a wire, then a current flows. And the current flow is proportional to the voltage difference delta V. But you can get a current even by having a change in temperature. If you have got two metals and you have a temperature difference between them, then you can generate a current which is proportional to the temperature difference. And that is what gives you the Seebeck effect, and the thermoelectric materials can generate electricity using this Seebeck effect. You can also have the converse effect, which is called as the Peltier effect, that when you pass an electric current through a junction, and then depending on the direction of the junction and some other intrinsic properties of the two materials, heat is either absorbed or released. And you can use this as refrigeration devices, if you like, or generate power using the Seebeck effect. Now, how do you improvise the efficiency of these materials? Because that is the main thing that you really want to do. And that is determined by what is called as the figure of merit, which is a measure of the efficiency of a thermoelectric material. So, as you see, the efficiency of a thermoelectric material, which is indicated here by a figure of merit, is driven by the two constants sigma and kappa. One is sigma is the electrical conductivity and kappa is the thermal conductivity. So their ratio is involved in determining the efficiency of these materials. And this ratio is a constant according to a law which is quite old. It was formulated in 1853 by Wiedemann and Franz. It's known as the Wiedemann-Franz law, that this ratio is a constant proportional to the temperature. The proportionality is the Lorentz number. What essentially this law tells you is that good materials which are good conductors of electricity are also good conductors of heat and vice versa, which is our common experience. But this law is not exact. It fails, and you really need to find out how to improvise the figure of merit of a thermoelectric material. This is where the mathematical modeling comes into the picture, because the constant sigma and kappa can be calculated using rigorous mathematical methods. So this is where the Lambert W function comes into the play. This is my student Akash working with Professor Valluri in my apartment after dinner. And Akash has done brilliant work in this. I'm very proud of it. So the constants of proportionality, kappa and sigma, these are determined in terms of certain integrals. And these integrals are called as Fermi-Dirac integrals because they appear in Fermi-Dirac statistics. There are corresponding integrals which are also known as the Bose-Einstein integrals, which come in the Bose-Einstein statistics. So these integrals have to be calculated, and sigma and kappa are given in terms of the Fermi-Dirac integrals. And this is Akash's paper, which is about 5 years ago, but in the last 5 years we have done considerable work since Akash's first contribution to this field. Essentially what we do is to calculate the exact Fermi-Dirac integrals and arrive at a generalization of the Wiedemann-Franz law, which I told you is not exact. It is a good approximation. It provides the limiting behavior, and you can get information about these mathematical functions from either the National Institute of Standard Technology, the tables, the NIST handbook tables, or tables by Abramovich and Stegen, for example. It is aimed at obtaining corrections to the Wiedemann-Franz law. And these corrections, you need to study the behavior of electron dynamics in metals, and that requires information, understanding about the scattering parameter. And in terms of the reduced chemical potential and the scattering parameter, you can determine these, you can carry out these calculations. You get tremendous insight into the mathematical expressions and determine a mechanism to optimize the figure of merit of thermoelectric materials. The thermal conductivity comes not only from the motion of the electrons, but also from the lattice component, the lattice vibrations, the phonon contribution. And the phonon contribution can also be evaluated much more accurately using this. The mathematical expressions are complicated. They involve the Fermi integrals, polylogarithm functions, and I will not get into these details. But that is something which, what I would like to underscore is the fact that Akash, whose picture I showed, started working on this project with me when I was a student at IIT Tirupati in the first year. So he was a first year student just like any one of you. And by the time he graduated, he had published this paper. Do you see your opportunity here? The first year students who are over here, I want you to recognize your opportunity over here. You can get involved in these studies. I will work directly with you. I will put you in touch with Professor Sriram Valluri. And you can contribute to frontier research even as an undergraduate student at the Vivekananda Institute of Professional Studies. So Akash calculated some of these Fermi-Dirac integrals and obtained these optimizing functions. You can see that there are various maxima and so on over here. So you actually get a scaling of the Wiedemann-Franz law. The K over E is a constant, K is the Boltzmann constant, but there is a correction factor which is the function A, which rectifies for the Lorentz constant, which is not a strict constant. And you need to do this by studying these maxima and minima in these functions. You can come up with mechanisms to optimize thermoelectric materials, their efficiencies. The other application of the complex numbers of the Lambert W function that I'm going to talk about is the applications in solar cells. Now, I'm sure everybody knows that this is an alternative source of energy that everybody is hoping to tap into. Now, consider this solar panel on the top of a car, and it converts solar energy into electricity which gets utilized in the car. It adds 5 kilometers per day of mileage to the car. Just imagine how many cars are running in every city, in every country, and the amount of advantage you will have. Now comes the difficult part. What happens to these solar panels when the car is going on a road like this? Every solar cell on that panel on top of the car is not receiving equal light all the time. Okay, because it will go under a shade of a tree, it will come out of the shade, and this is happening dynamically. Now what happens to the solar cells? Now they are acting in series, and if one solar cell is generating electricity which is not able to pass because there is a shade, a transient shade, okay, it's going to create heat and the solar panel can get damaged. Now this is a big problem. So you need to model this, and modeling this involves mathematics. This is done using complex functions, using the Lambert W functions, the polylogarithm functions, and these have been studied in our research group. So to mitigate situations of this kind, you need to do a lot of simulation work, very advanced mathematics. This is again done by students at IIT Tirupati. Sibi Balan and Prabhat again started when they were first year students. So Akash is not the only one. There are plenty of opportunities. I've done a lot of work with undergraduate students. And I hope that we will have that culture right here in this hall. Not just Prabhat and Sibi Balan, the third author, the first author is Prabhat, second is Sibi Balan, the third is Aditya Chaudhary. I did not have Aditya's picture over here to show, but he was also their classmate. So Prabhat, Sibi Balan and Aditya have played the lead role in this. They have determined the efficiency of solar cells using the Lambert W and the log right functions. When you use the logarith functions, you get certain numerical problems, you run into some numerical overflows and so on, and how you go around it is by using the logarith function, which is the work which was done by these 3 students. Very nice work. So they generated algorithms, did calculations. These have been published in a conference in South Africa last year, and then it came out in an IEEE journal. It's very exciting when you see undergraduate students publishing work of this quality. So, as I mentioned, they help improve the numerical accuracies in this. These are some of the other students. On the left, is Akash. Then next to him is Pranavchandra. Next to him is Harsh. Harsh was a student at IISER Tirupati. He also started working with me when he was in the very first year, just out of high school. And by the time he comes to the 4th year, in those 2, 3, 4 years, they learn all the mathematics, the physics, the applications, the numerical methods, the computing, building the algorithms. And by the time they get to the 4th year, they publish something like this. This is amazing. I'm very proud of this one. Next to Harsh is Professor Sriram Valluri, who is the main expert in this field. He's one of the world's leading authorities on the LabW function. I'm very privileged to have his support and have his guidance. So I've been working with Sriram Valluri for more than a decade now. Our collaboration started in 2011. And this is Aditya. He's one of the authors of the previous paper who I mentioned. So what they have done, this paper, they've developed mathematical models to simulate the behavior of solar cells using the logarith function, which is a transformation of the Lambert W. And it improves accuracy and speed of these calculations. So I think this is my last slide. The first picture is that of a quantum well. It's a particle in a box kind of thing in 1 dimension, which some of you may be familiar with. This is the problem for which Ken Roberts and Sriram Valluri provided solutions using the Lambert W functions. Otherwise, they are amenable only to numerical or graphical methods. The second figure is roughly the opposite of the previous one. It has a potential barrier, and one of the mind-boggling phenomena in quantum theory, it is actually a mind-boggling phenomenon in nature, that even through a barrier, a particle can tunnel through. That's called tunneling through a potential barrier. And this has got certain similarity with optical properties, which is called as frustrated total internal reflection. Right now I'm working on the frustrated total internal reflection which is with another student from IISER Tirupati. He did this work a few years ago, a student by name Zadhav. So he has done some very good work. We are writing that paper now. This has got important applications in modeling quantum dots, microelectronics, and even metamaterials. So these are very fascinating applications of these methods based on the Lambert W function. And I told you that I will comment on the importance of mathematics, which is going to be a quotation from Eugene Wigner, and I am going to end my talk with this quotation. So Eugene Wigner, he wrote a paper in 1960. The title of the paper is The Unreasonable Effectiveness of Mathematics and Natural Sciences. It's almost unreasonable. It's shocking, but it works. And what he wrote in this paper is that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. It is a wonderful gift. It is a very powerful gift, and it is up to us to use it. It's a very powerful gift. I talked about complex numbers, complex analysis. I talked about quantum theory. The quantum theory is basically a mathematical framework to describe the laws of nature. It's based on linear algebra. But it works. Do we really understand it? We don't. In fact, Feynman went on to say that nobody understands quantum theory. Niels Bohr said that if you're not shocked by quantum theory, then you have not understood it. We don't understand all the intricacies, but we can use it. Thank you very much. If there is any question or comment, I will be happy to make an attempt to respond. Yes, please.
Thank you, sir. It's a very eye-opening talk. Learned a lot of things here. So I have two questions, sir.
Yes.
You talked about the polyamide material, which is stronger than steel. So this polyamide material is also used for membrane in the reverse osmosis distillation system.
Yes.
So the problem there is to have a membrane which will require lesser pressure to sustain. So is that something done on that aspect?
I do not know, but I presume that it can be studied. I'm not personally aware of a specific application in the area that you are talking about.
Yes.
But that's something that I can talk to my colleagues and find out if they know anything about it. You have one more question.
One more question is, I just also learned about this new material for thermoelectric generator.
Yes.
So this is figure ZT, figure of merit.
Yes.
So whatever work I understood is this was basically the already developed Lorentz number is there.
Yes.
So and your work is basically a new equation for that Lorentz number.
It provides a correction to the Wiedemann-Franz law.
Okay.
So with the Wiedemann-Franz law involves the ratio of the thermal conductivity and the electrical conductivity.
Okay.
And the proportionality involves the Lorentz number. So the Lorentz number is a universal constant. But then there is a correction to it, which can be obtained using the methods, the mathematical modeling that we have done. Because what we do is the mic on? Yeah. So the mathematical modeling that we have done, it calculates the conductivity, the thermal conductivity and the electrical conductivity using rigorous mathematical functions, which are the Fermi-Dirac integrals.
Okay.
And the polylogarithm functions. So using this, you can calculate the ratio much more exactly. So the Wiedemann-Franz law gets modified, gets corrected,
okay.
And then you can determine the efficiency of the thermoelectric material appropriately. Okay. That's
Sir, is there any new material or new development on the materials to improve ZT?
Okay, so that's a very good question, and that's exactly where our collaborator Ajay Soni comes into the picture. Ajay Soni is an experimentalist. He is at IIT Mandi. He's on the faculty there, a good friend of mine. And using our formulation, Ajay is now trying to build new materials which can reproduce some of the advantages which come out of these calculations. So we have not succeeded at that as yet, but Ajay is putting in a good amount of effort in this. This is where we really need collaborations, because it is impossible for a single person to have capabilities in experimental science as well as theoretical science, computational skills, and so on. So we are very fortunate to have this collaboration in which we have experimentalists from IIT Mandi and a theoretical group from the University of Western Ontario. So I hope that we will have something to report coming from Ajay's lab. Thank you. Any other question or comment? But I'm very easily reachable, so feel free to send an email to me and so on. So Vinit ji has my contact. So thank you very much.